One small grain of moon dust means one giant leap for lunar studies. This is from the Field Museum. Scientists have found a new way to analyze the chemistry of the moon's soil using a single grain of dust brought back by Apollo 17 astronauts in 1972. Their technique can help us learn more about conditions on the surface of the moon and formation of precious resources like water and helium. Back in 1972, NASA sent their last team of astronauts to the moon in the Apollo 17 mission. These astronauts brought some of the moon rock back to Earth so scientists could continue to study lunar soils in their labs. And since we haven't returned to the moon in almost 50 years, that's another issue. Every lunar sample is precious, and we need to make them count for researchers now and in the future. In a new study in meteoronics and planetary science, scientists found a new way to analyze the chemistry of the moon's soil using a single grain of dust. Their technique can help us learn more about conditions on the surface of the moon and formation of precious resources like water and helium. We're analyzing rocks from space atom by atom, said Jenica Greer, paper's first author and PhD student at the Field Museum and University of Chicago. She said, "It's the first time a lunar sample has been studied like this. We're using a technique many geologists have not even heard of. We can apply this technique to samples no one has studied." Philip Heck, curator of the Field Museum, associate professor at University of Chicago, and co-author of the paper, says, "You're almost guaranteed to find something new or unexpected. This technique has such high sensitivity and resolution, you find things you would not find otherwise and only use up a small bit of the sample." The technique is called atom probe tomography, APT. It's normally used by material scientists working to improve industrial processes like making steel and nanowires, but its ability to analyze tiny amounts of materials makes it a good candidate for studying lunar samples. The Apollo 17 sample contains 110 kilograms, that's 225 pounds, of lunar rocks and soil. The grand scheme of things, not a whole lot, so researchers have to use that wisely. Greer's analysis only requires one single grain of soil, about as wide as a human hair. In that tiny grain, she identified products of space weathering, pure iron, water, and helium that formed through the interactions of the lunar soil, and the space environment. Extracting these precious resources from lunar soil could help future astronauts sustain their activities on the moon. To study the tiny grain, Greer used a focused beam of charged atoms to carve a tiny, super sharp tip into the surface. This tip was only a few hundreds atoms wide. For comparison, a sheet of paper is hundreds of thousands of atoms wide. She said, "We can use the expression nano-carpentry," Phillips Heck said. "Like a carpenter shapes wood, we do it in a nanoscale to minerals." And once the sample was inside the atom probe at Northwestern University, Greer zapped it with a laser to knock atoms off one by one. As the atoms flew off the sample, they struck a detector plate. Heavier elements like iron take longer to reach the detector plate than lighter elements like hydrogen. And by measuring the time between the laser firing and atoms striking the detector, the instrument is able to determine the type of atom at the position and its charge. Finally, Greer reconstructed the data in 3 dimensions, using a color-coded point for each atom and molecule to make a nanoscale 3D map of the moon dust. It's the first time scientists can see both types of atoms and their exact location in a speck of lunar soil. While APT is a well-known technique in material science, nobody had ever tried using it for lunar samples before. Greer and Heck encouraged other cosmochemists to try it out. They said it's great for the comprehensively characterized small volumes of precious samples. We have these really exciting missions like Hayabusa 2 and OSIRIS-REx returning from Earth soon, uncrewed spacecrafts collecting tiny pieces of asteroids. This is a technique that should definitely be applied to when they bring back the samples, because it uses so little material but provides so much information. Studying soil from the moon's surface gives scientists insight into the important force within our solar system. Space weathering, space's harsh environment, tiny meteorites, streams of particles coming off the sun, and radiation in the form of solar and cosmic rays. While Earth's atmosphere protects us from space weathering, other bodies like the moon and asteroids don't have atmospheres. As a result, the soil on Mars, on the moon's surface, has undergone changes caused by space weathering, making it fundamentally different from the rock that the rest of the moon is composed of. It's kind of like a chocolate-dipped ice cream cone. The outer surface does not match what's inside. With APT, scientists could look for differences between space-weathered surfaces and unexposed moon dirt in a way that no other method can. By understanding the kinds of processes that make these differences happen, they can more accurately predict what's just under the surface of moons and asteroids that are too far away to bring to Earth. Because Greer's study used a nano-sized tip, her original grain of lunar dust is still available for future experiments. This means new generations of scientists can make new discoveries and predictions from the same precious sample. 50 years ago, no one anticipated that someone would ever analyze a sample with this technique and only using a tiny bit of one grain, Heck states. Thousands of such grains could be on the glove of an astronaut, and it would be sufficient material for a big study. Greer and Heck emphasize the need for missions where astronauts bring back physical samples because of the variety of terrains in outer surface. Quote, if you only analyze space weathering from one piece of the moon, it's like only analyzing weathering on the Earth on one mountain range, Greer says. We need to go to other places and objects to understand space weathering in the same way we need to check out different places on Earth like the sand in the deserts and outcrops in mountain ranges on Earth. We don't yet know what surprises we might find from outer space and space weathering. It's important to understand these materials in the lab so we understand what we're seeing when we look through a telescope, Greer says. Because of something like this, we understand what the environment is like on the moon. It goes way beyond what astronauts are able to tell us as they walk on the moon, and this little grain preserves millions of years of history. The results from this study convinced NASA to fund the Field Museum and Northwestern team and colleagues from Purdue for the next 3 years to study different types of lunar dust with APT to quantity its water content and to study other aspects of space weathering. Funding for the work was approved by the Taiwanese Foundation and Natural Science Foundation, the Office of Naval Research, Northwestern University, and the Field Museum Science and Scholarship Funding Committee. Materials provided by Field Museum, and this is on Science Daily. If you'd like to join me on my Patreon account, you will hear content not covered by mainstream media. These riveting stories will be based on my research, and I will state my opinions and give my personal insight on diverse and controversial subjects and world events not covered by mainstream media, and not supported by YouTube guidelines. So whatever I have on my Patreon, most of those will not be on my YouTube channel. Please consider becoming a member today. More of the most significant and important videos will be on my Patreon channel. Your support helps me to continue my research and keeps this YouTube channel alive. And we depend on your support, your generous charity, because we help economically challenged families here in Athens, Greece, in Kapota, and we also help the young generation with university tuition and the community around our church. Thank you.